Huh. It's actually working. Okay. So, forces. Interesting. So, we're on page 356. You guys have already done a little bit of work with force when we did the static versus kinetic friction. Friction is a force. In fact, you might say that friction is the F word of physics. Because it's just the big bad. If we're talking about motion, that's the first thing we talk about with physics. Friction is a force that opposes motion. So it goes back to, well, what then is a force? Usually people would say that a force is a push or a pull, and it generally causes something to move, to have motion. Or, in the case of friction, what does it do? It opposes motion. If there were no friction, then once you got something pushed or pulled, it would continue to move until something were to stop it. What's that?
You wouldn't be able to dance because you fall.
You wouldn't be able to do anything.
Watch the video in fourth grade.
No, you wouldn't.
Dancing, doctor.
It's true. It's the same way with just walking. If you, oh dear, how do I do this now? Oh dear. Does it work now? That's the same thing. So if there were no friction, then I certainly couldn't walk because I use the friction of the floor to push off of the floor and propel my body forward. I push on the floor pushes on me. If there's no friction between the floor and myself, then as I pushed on the floor, I would just keep on slipping, like you do with ice. Because it has a lower coefficient of friction, ice is slippery. If the ice were completely frictionless, then you wouldn't be able to push off of it at all and move at all. Question?
If friction didn't exist, theoretically, wouldn't we, like, die?
Yes.
Because our innards would be like, no friction.
No friction. Yes?
Nice.
Just like your socks have no friction?
Socks have a lower coefficient of friction than your toe pads.
Because especially here, like on these kinds of boards, it's just like a lot.
Right.
Yeah.
Yeah.
There's not no friction.
It's one of the reasons why you need to wear closed-toed shoes in the lab. I don't want you slipping in my lab. Yes?
But if there was no friction in the world, couldn't you like just set up big barriers? Because you could like sort of hug it because you don't need friction as long as the area.
Yeah, but that thing would have no friction, so
is smaller.
all
You
the
die
screws
before you
and
could do
bolts would
anything,
not, like,
Jonathan.
be-
Yeah,
they wouldn't stay.
your innards would blow up.
Without friction, you wouldn't be able to hold on to that.
You wouldn't be able to do anything, you'd die.
And the barrier's right here.
And then you would slide
I
up.
don't know how you make
No,
that.
gravity would still
Body try.
Jonathan, how would
Guts
you
would
get
go
the
in.
barrier there?
Corey,
okay,
thank you.
Thank you for that wonderful image. That's the second most perfect image, but I'm stuck in my head.
If you try to hug it, you're hugging it, you end up like moving up or down. No, but you'll be moving up or down.
Oh, yeah. Thanks for that. Yeah.
Because then you're moving up or down. So eventually.
Okay. Now, force is measured in a unit called a newton, after Sir Isaac Newton. It's represented by a capital N. You could also break it down to kilograms, meters per second squared. And, well, these two are equivalent, a newton or kilogram times meter per second squared. So that's something to recognize. And like other things, like velocity, you can actually combine forces. So if you were to take a box that was, so let's say 100 newton weight box, and Sally were to give it a 10 newton push, and Bobby was to give it a 20 newton push, then what kind of push is this 100 newton box experiencing?
Well, the bottom is going to go out, and then it's going to, like, tip back.
Well, how big of a force is it experiencing?
30 newtons.
30 newtons, right? Because you just take the 10 newtons plus the 20 newtons, and you get, sure enough, 30 newton push in this direction. Now notice I'm also doing a direction with this. So what type of unit is force?
A vector.
It's a vector because not only does it have quantity, but it also has direction. So forces are vectors, and you guys kind of looked at that when you were looking at the static. So you had, one of the questions was to draw a force diagram. So you had the normal force, right, of the lab table pushing on the box. You had gravitational force, right, that gravity was pulling on the block that you're using. You had a force meter pulling this way, and what force was in this direction? What was opposing the pull?
Friction.
Friction, exactly. So that one was friction. So you had all these forces working on that wooden block. Right?
Yeah, and then on the right is the people pushing, right?
Mm-hmm, exactly. So you have to bear in mind the direction that things are happening when you're talking about forces. Yes?
Then what's the up and down one?
The down was gravity, and what was going against gravity?
The sun's gravity.
The force of the tabletop pushing up on the block. How do we know that the tabletop was pushing on the block? What's that? Well, there must have been a force opposing gravity, otherwise the block would have fallen right through the tabletop. Right?
Oh, matter.
Same thing. Here we have a whole bunch of kids who are, let's see, sitting at a device that looks kind of like this, right? And they're sitting here. So how come these people, they're diligently taking notes, how come these people don't just fall to the ground?
Matter there. There's something there.
And what is that matter doing?
Pushing up.
It's holding you up. It's fighting against gravity. You have gravity that is pulling you down, and you have a seat that is pushing you up. Yes, if the seat doesn't push you up enough, then you fall to the ground. And that's what happens a lot of times when
Somebody loosens the bolts.
fat people fit on things that do not support their weight. Right?
So
Or it could be, you know, kids come in with their books, they sit down, they smash it down, and eventually they fatigue the metal. And eventually even small people. Not here, no. It would take a lot of metal fatigue. Or it could take some, you know, metal-eating nanobites. But we don't talk about that.
Yes. We're not going to talk about that.
What is
Yeah, eventually.
Would friction fall into the Newton's law where reaction is an opposite reaction?
Oh, yes, we'll get to that in just a moment. Let's talk about the types of friction. Oh, dear. Let's see if we can go to the next one here. Nope. Nope. Oh, very good. Okay, so let's talk about types of friction. We have sliding friction, which you guys investigated the last couple days. We have static friction, which you guys investigated. And we also have fluid friction. Oh, sure, let's do rolling. And we have rolling. So, static friction, you already mentioned that. What does static mean?
Standing still.
Standing still, right? We have sliding friction, and that one's going to be what, Maxon?
Sliding when you're going across things without friction.
Exactly, when you're sliding. What about rolling friction, right? When you're rolling. Fluid friction.
When you're going through water.
Liquid. Okay, so he mentioned sliding. Did you say sliding the block, Maxon? Is that what you said?
No, I said when you're going across something smoothly.
Okay, so let's say you're actually going across something smoothly. Let's say you are sledding. So sledding is an example of sliding, right? Static friction, that's where you are not moving.
Wait, do you have static friction right now?
Rolling friction, what's an example of rolling friction? Yes? Okay. A ball going down a hill. And fluid friction?
Water in a sloshing cup or something.
Okay. Water in a cup?
Wait, does a boat have fluid friction if it's like on the water?
Yes. The boat experiences fluid friction as it goes through the water. So, of all of these, let's rank them in order. Which one is the greatest in terms of magnitude? All other things being equal. Taylor, what do you think?
Is it static friction?
It is static friction. So this is number one, big bad guy. It's really hard to get things moving in the first place. Once you get them moving, it's a lot easier to keep them moving. What's number two? Yes.
Sliding.
Sliding friction is indeed number 2. Now we get down to rolling and fluid. This is tricky. McGrath. Rolling is 3, and fluid is 4. So let's take something like, let's take something like Mr. Shoes has some new boots, and he wants to move along, right? So what I could do is I could just shuffle along in my new boots, right?
Then you're sliding.
But then it doesn't really do much. So how am I going to reduce this friction because I'm not moving much?
Lift your feet.
Yes? I could do that.
Or
Or I could roll, right? So if I put some, look at that. I'm going to put, they actually make shoes like that, don't they? They have a little rollers in them. Wheelie thing. So, I know it's out of fashion now, but you can do that, right? You put wheelies on your shoes, and you still need some friction to push off, right? And so you kind of push to the side, get more friction that way. Then you roll with just one push. I suppose right now I push, and I stop. And I push, and I stop. Put wheels on, and I'm going to roll for a while, right? Well, how can I reduce the friction of that rolling?
By
water.
Adding water.
putting a lubricant on the wheels.
Yes! So, not water, but a lubricant, which happens to be a fluid.
Butter.
Usually,
Yeah, you put butter on.
oil. Because which has lower coefficient of friction, water or oil?
Oil.
Oil. So I'm going to oil my bearings, right? And then I'm really going to go, right? I'm really reducing the friction here. Instead of going like this all day, I'm flying down the hallway. McDougal can't catch me. Right? Try as you might.
There's a lot of friction, right? What if she gets on like it's really hard
Yeah,
to
I suppose that would generate its own kind of friction, though,
what if
wouldn't
she
it?
gets what if she steals
Okay.
What if she's still
How is he still
I get to
stands right
Yeah.
there?
Okay.
Where
So-
did you get them off of?
Let's take a look at something else. Falling. Falling, things fall towards the center of the mass of the Earth due to the gravity involved. So since Earth has a lot of mass, it has a lot of gravity. As far as we're concerned, the acceleration due to gravity is around 9.8 meters per second squared. Right? Or you could say meters per second. So every second that goes by, I'm going to go 9.8 meters per second faster.
Even for everything. So.
Everything. Because the problem is, you'd have to say it's for everything because you couldn't say that suddenly the mass of the Earth is going to change just because the object is different. Right? Because the thing that's causing the gravity in the first place is the Earth pulling on the object. Right? And so if you were to say that, let's say you take Mr. Schuth versus the whole school. Right? And you take us both up 100 feet and you drop us. What's going to cause us to fall? Gravity. And what causes gravity?
mass times mass of the
pull.
distance squared.
The pull of the mass of the Earth, right? So we're both going to be pulled by the same Earth, right?
Yeah, but the reason, like, if it was higher, the school would be first because it has a higher terminal velocity.
Terminal velocity. Oh, I'm glad you brought that up because there is a force here on the Earth that counteracts this gravity, and that is the...
Air resistance.
It starts with an F again. Friction. That bad word. So it's the friction. In this case, it's the friction of the air. These air molecules that we have to push out of the way as we go through the air causes friction. It's a force that opposes that motion. Yes.
So when the terminal velocity is when the friction of the air equals the mass of the thing falling, right?
The terminal velocity is the velocity at which the force of gravity equals the force of the air resistance. Yes. Or once the air resistant force has... once the air resistant force has equaled your weight,
Yeah.
which is the force of gravity on your mass, then you reach terminal velocity.
That's what that stupid myth about the penny and the Sears Tower is done.
This is correct. Because pennies have very low mass. Very low terminal velocity. What's that? Ooh, thank you. We better stop that.